All right, so we have a number of folks that have already started logging in. Again, today's webinar is going to be recorded. So, in terms of the webinar, be considerate, respectful, collaborative, keep muted unless the facilitator calls on you to speak, and maintain a supportive and positive environment and respect any questions or input from other participants. I believe today we'll have clarifying questions after the speakers, but then we have a significant amount of time after discussion. And so today's topic, energy and AI. Our speakers, Casey Burleson, Stephanie Morris, and Kendall Mongard. And in terms of this is part of the broader multi-sector dynamics initiative, so a transdisciplinary research area where we're seeking to better understand human Earth system feedbacks and how they shape key societal systems across scales and uncertainties. So this is part of a broader initiative to build a community of practice, and our webinar series, our activities, and our working groups have all been sort of formulated to help accelerate the development of needed foundational capabilities in human Earth system science through open science and growing a transdisciplinary workforce. If you'd like to find out more, you can go to our website here. You have the QR code. We're also on LinkedIn. And so there's a number of resources here. Feel free to reach out to the facilitation team. And with that, I'm going to stop share and pass to Casey. And again, thank you to our speakers for an exciting webinar today.
Thanks, Pat. Can somebody confirm that they can see my full screen?
Can see it.
Perfect. Ooh. Okay. So thanks, Pat, and the other members of the facilitation team for inviting us to share some of our results today. This is work that we've been doing in the IM3 and GSIMS projects, which are funded out of the multi-sector dynamics portfolio and DOE's BER. And so I'll kick us off by providing an overview of the interactions between energy and AI, and then I'll pass to my colleagues Stephanie Morris and Kendall Mongard, who are going to go into some detailed analyses that we've been doing over the last few months in this angle. So for the intro, I'm going to draw largely from this report that came out a few months ago from the International Energy Agency. It's called Energy in AI. So unless I attribute a different source, this is where this is coming from. And this report starts off with a really nice summary where it talks about the uptake of artificial intelligence over the last few years and the role of energy in supporting that growth and demand for AI. And they had the shocking quote, or this quote in their overview: "There is no AI without energy, specifically electricity for data centers." And that's really sort of the motivating force behind the work that we're going to show today. So in terms of artificial intelligence, like if you've been following the news at all, I'm sure you know that there's just been an explosion in AI tools over the past few years. AI has been around for quite a long time, but what I would say is like the potential of AI is finally being realized. So what I'm showing in this plot from the report is the accuracy of standardized AI models against benchmark standards over the last 6 years or so. And you can see that across standards related to coding, scientific understanding, mathematics, and visual interpretation of figures, there's this sort of up and to the right trend where you get these really nonlinear growth rates and the ability of the models over the past several years. And I think if you've tried to use these tools in your work, you can obviously see the potential impact that they can have in supporting the work that we do. The report had these really nice figures showing that this step change in the performance of artificial intelligence is due in large part to widely available cheap computing. So the two graphs here show time series on the left of the cost of a compute node, a GPU compute node normalized to the year 2006. And that cost has dropped by over 99% in the past 2 decades. And likewise, on the right, it's showing the model training size index, which is like the amount of computational power used to train state-of-the-art models. And if you index that to 2014, meaning a value of 1 is in 2014, the most recent models, as of the writing of this report in 2024, were using about 350,000 times as much computing power to train the models as they were a decade ago. So really, there's a huge amount of data out there. It's cheap compute, and you combine those two, and you're able to train the models in much more complex ways using larger samples of data, and that's driving sort of their increase in fidelity and robustness. But with all this power comes great responsibility, right? So you have all of these projections that are starting to matriculate in the gray literature and also the peer-reviewed literature, looking at the need for new computing centers or data centers to support generative AI, and also to a lesser extent, things like crypto mining. And there's a couple of patterns in these projections of the need for new data centers. One is they tend to be really large. So like this EPRI report that came out last year that Kendall will talk more about suggests up to like a 15% annual year-over-year growth in electricity demand due to data centers in the United States just within the next decade. They also tend to be very uncertain, right? So as we get more information, as new models are developed, like the DeepSeek model that came out earlier this year, some of those usage projections get sort of called into question, right? Because some of the models use different training paradigms that may use less electricity demand compared to some of the chat GPT type models on which these projections are based. So you combine the growth in data centers to support AI with growth in electricity demand driven by trends like domestic manufacturing and electrification of end uses like heating and transportation. And you really see like these unprecedented growths in electricity demand in the United States. So anywhere between 35 and 50% in the next 15 years, according to this ACP report. Another angle with data centers that sort of comes out in these reports and that Kendall will touch on in her work, I think Stephanie as well to a lesser extent, is that data centers are also potentially very large consumers of fresh water. So a lot of them are being built with water-cooled systems where they use water flushed through pipes to actually cool down the computing racks. And some of that water is consumptive use. So as you build more and more of these data centers across the United States, we need to start taking into account their impact on fresh water. So as you grow these loads, combined with things like scheduled retirements of generators, you get this sort of imbalance in the projections of electricity supply and demand. And that came out quite clearly in this NERC report that was published in December of last year, where they were looking at a long-term reliability assessment of the US electric grid. And they looked in different parts of the country, what are the primary drivers of demand growth? That's what's being shown in the map there on the left. And data centers are those blue icons. You can see in pretty much every region of the United States, with maybe the exception of Florida and the Northeast, the growth in data centers are a primary driver of demand growth in these regions. And that includes places like PJM and the Eastern Interconnection, which covers areas such as Philadelphia. And what this report says, the quote up here shows that demand growth is now higher than at any point in the past 2 decades. And that's increasingly being driven by these large industrial and commercial loads. So if you combine that demand growth with the planned retirements of these generators, the trend is to reductions in reserve margins, or sort of excess capacity in the system to meet demands. And that's what's being shown in the table. So the different rows represent different regions of the country. And then the different columns are projections starting in the year 2024 out for the next decade of the reserve margin, or sort of how much headspace is available in the electricity system. And typically, these entities build to something like peak demand plus 15% or peak demand plus 20%. So anything with a reserve margin in this table over 20% is deemed to be adequate. And anything below that is when you may start to have imbalances in supply and demand. And what the table shows is that over the next 5 years in many regions, and maybe out to 10 years in some regions, those reserve margins drop off quite drastically to where, 6 or 7 years in the future, you have reserve margins falling below that 20% margin in many regions of the country. And in some places, it even goes negative, meaning the projected demand for electricity outstrips the projected supply. Another issue being faced by the utilities is that these data centers are typically being built quite quickly. They can come online in just a few years. So from choosing a site to building the thing to connecting it to the grid, that's really like a maybe 2-year time window. It takes a lot longer than that to actually build new generators or to do transmission upgrades to support those new facilities. So really, if you ask the folks in the utility industry, what they'll tell you is that most of the data centers built to date have taken advantage of existing headspace on the grid, meaning like they're not building new generators explicitly to meet that demand. But we're basically out of room or quickly running out of room in many parts of the country, meaning that if we continue to add these large loads, we're going to have to build new generation and transmission to match that. And it takes a long time to do that. And that was really nicely described in this WEC report, which came out in February of this year. So all these driving factors sort of give the impression that utilities are scrambling to adapt. And if you just do Google searches on this, you can find these really sort of eye-popping quotes like this one from Salt River Project, which is a utility down in the Arizona area, where they had a quote earlier this year where they said, it took SRP 120 years to develop the generation capacity we have today. We need to double or triple that capacity in the next decade in order to be able to meet that forecasted demand growth. So really, these are sort of monumental changes for the industry in terms of demand and then building the generation that they need in order to meet that demand. And the AI industry is well aware of these limitations, right? So Sam Altman gave testimony to the Senate just last month, where he was talking about the need to address some of these imbalances and to build new energy capacity in order to meet the demand of data centers. And so in his testimony, he had this quote that said, the cost of AI will converge to the cost of energy. The abundance of it will be limited by the abundance of energy. So what they think from like a technological perspective is that truly like the cost to use tools like ChatGPT and other artificial intelligence tools is really going to depend on how much it costs to produce the electricity to power these data centers to support the industry itself. This is a big deal, and DOE is taking this quite seriously because it matters where these facilities are being built. So this is a map from this IEA report that came out showing like the US is obviously a key player here, but you also see lots of data centers being built in Western Europe and in Southeast Asia, places like China and Singapore. And our secretary, Chris Wright, the Secretary of Energy, has compared this to something like the Manhattan Project, where it feels like a race, right? And he says it's a race that not that you want to win, we had to win. And I think AI has a similar overlay. And when you sort of read into his comments in other areas, they're not coming at this from like a America first perspective, like we have to be the best. They're really thinking of it in terms of there's a national security implication of not having these facilities in the United States. So certainly people are using ChatGPT to build things like cat memes and things like that. But we're also using it to support our business infrastructure, right? Like basically every major industry in the United States is starting to deploy AI to support the work they do on a day-to-day basis. We're also starting to use AI to support things like critical infrastructure, like operating the electric grid itself. And so when you build all these critical services on top of artificial intelligence, you really need to control the generation of that artificial intelligence or have the capability to control that so that you can manage the security risk associated with this. I think you can frame an analogy to like the microchips crisis that we had during the early parts of the pandemic, where imports of microchips really shut down. And a lot of industries were panicked by that. And that drove this sort of realization that we need to control the domestic supply of microchips and be able to produce them in the United States for things like national security. The final thing I'll close with is talking about the interactions. And as I said, one of the interactions is the demand for water to support these data centers. So the report goes back and looks at what's on the ground now in 2023 and then projects forward in time things like withdrawals of water, which are mainly used to generate the electricity for the data centers, and consumption of water. And here you see breakdowns where you still do get consumptive water use due to things like generating electricity, but there's also a fair amount of consumptive water use for the cooling themselves. So depending on where you build these things in the country, and Kendall's done a really nice analysis of this, you could add a water stress to systems of the US that are already stressed due to things like agricultural irrigation or municipal uses. So that's something to keep in mind. And the final thing on a bit of a more hopeful thing is that the interactions between energy and AI are not all unidirectional, right? Like it's not just we're providing energy for AI. The energy system itself stands to benefit from artificial intelligence. So the report talks about things like using it to optimize our planning cycles and using it to optimize things like the operation of the grid itself. And then from more of a R&D perspective, you could use AI to do things like accelerate innovations in battery technology through supporting material discovery or production efficiency research for things like batteries. So there is some reason for optimism there. So why are we talking about this in a multi-sector dynamics webinar? And I think that we can make the case that the energy sector data center risk is really a classic multi-sector dynamics problem. So hopefully if you're on this webinar, you've read this paper by Read It All that we published in 2022, which really defined multi-sector dynamics as a field. And we had this canonical icon here that's come to be known as the peacock diagram, where we talked about like what are the different flavors of multi-sector dynamics in terms of like the systems that we're studying and how they integrate with each other, but also in terms of like what are the methods that we're using in order to study these multi-sector, multi-system interactions. And if you go back to some of these risks that we've raised from the growth in data centers, they map directly onto this diagram. So you can think about these as systems of systems problems where you have these interactions between energy, water, and the economy. You can look at things like economics in terms of supply chains and international trade. And then if you look at the specific methods that we're using or some of the analytical challenges, you discover that we're facing things like adaptive responses, where the choices that we make in terms of like building the system out really determine the future, and those choices are quite uncertain. You also have challenges related to regulatory uncertainty and risk, and path dependencies, where we may be locking into certain paths based on the decisions that we're making now in terms of how to support this growth. A lot of the analytical challenges also map. So you have things like data limitations associated with the rapid onset of highly nonlinear growth rates and demand for data center computing. And then we also face challenges just in terms of the data that's available to do this research. So there's a lot of proprietary and business sensitive data out there that makes it harder to do this work. So once we figured out like this is an MSD problem, and I think I and others were sort of pushing this trend for the last few months, DOE came to us in February and asked the IM3 and GSIMS projects, all right, what capabilities can you guys bring to bear to study this problem? And so that was really driven by Bob Valerio, who stepped away from DOE, coming to us and recognizing this as an important problem and asking us to do the research to support the work. So I'm going to hand it over to Stephanie Morris first, and then to Kendall Mongard, who will show you some of the preliminary results that we've got digging into this energy and data center interactions work using multi-sector dynamics tools. I'll stop sharing and I'll hand it over to Stephanie.
Okay, thanks, Casey. All right, can you confirm you can see my screen?
Okay.
Great. Okay, so I'm Stephanie Morris. I'm presenting on behalf of our GSIMS team, Tom, Mengchi, Pralit, and Marshall. And today I want to share with you our initial explorations into the implications of AI and data center service demand on the energy, water, and economic systems. But I'm going to be focusing primarily today on energy and water. So it's, for all the reasons Casey just described, it's really becoming important to understand the energy, water, land, and economic implications of data centers. But to analyze the potential for growth in data centers, including their size and the energy and water requirements, it's really essential to understand what the drivers of data center expansion are. Specifically, it's the services they provide. So these services have changed really dramatically over the past several years, and they're projected to change even more with a rapidly increasing share of data center electricity being used to provide AI services. However, again, Casey just described how resource intensive these data centers are. And the growth in data center capacity needed to meet this increasing demand may bring enormous challenges to future demands in multiple sectors. So energy, water, capital, land, and critical minerals. And because of the potential scale, role, and impacts across so many co-evolving parts of the economy and physical systems, we really need a comprehensive analysis of future scenarios of AI and data centers. And this requires a long-term multi-sector dynamic modeling approach. So again, as Casey just mentioned, it's really quintessential MSD research. And it's been enabled by many years of multi-sector dynamics research that's been funded both by the DOE Office of Science and many other sponsors. So first, I just want to give a quick overview of our general approach to this work. So we start with the fact that data centers exist to provide services, services such as computing, storage, artificial intelligence, both the training and inference needed for that. Providing these services then requires data centers, and the design of those data centers will vary depending on which types of services they provide, with traditional data centers focused more on traditional IT service needs like email and storage, and large hyperscale data centers targeted more toward AI services and cloud computing. So different types of data centers will have different energy and water intensities and different requirements for land and proximity to users and infrastructure, and also the critical materials necessary to build the types of servers in the different data centers. So the future impacts of data centers depends on understanding both their consumption of electricity, water, and other resources, and how the demand for those services could evolve. And a key part of this includes those two-way interactions that Casey mentioned. So this isn't just, demand for services, but those services are actually providing something to the economy and have implications for the broader economy, for trade, for jobs. So I'm not going to try to give a full detailed overview of the modeling details in GCAM, the Global Change Analysis model that we're using for this analysis. But I do want to point out that we're modeling multiple data center services, specifically traditional services, as I mentioned, like email and storage, and cloud computing and AI. And these have different building types. With hyperscale data centers tailored more toward cloud computing and AI. There's different IT technologies used in those data centers to provide the different services, and those technologies have different efficiencies, costs, and cooling requirements. And we're also modeling different cooling technologies, which themselves have different costs and water and energy usage. We're also exploring the indirect water from the electricity generation used to power the data centers. And we'll be looking at potential implications of hyperscale data centers, either drawing electricity from the grid directly or from on-site generation. So the research gap here is that data center services and buildings will change in the coming year. That has implications for multiple sectors, both in competition for resources and potential feedback to economic development. And we really need to understand this, these feedbacks and competition across sectors better. And our modeling approach allows us to look both at the near-term impacts and longer-term implications from changing demands for the drivers of data center services and the improvements in technologies used to provide those services. So the research questions we're looking to explore are things like, what are the key processes, drivers, and uncertainties impacting the future growth of data center services and data center expansion? What effects could AI have on economic growth through changes in sectoral feedbacks and labor productivity? How will electricity, water, and land systems be impacted by data center and AI expansion? And what physical constraints might limit the growth of data centers? So now I'm going to share some early GCAM results that quantitatively illustrate some of the questions we're addressing. For this work, we modeled the effects of 4 different parameters in GCAM. We looked at the service demand, which is how quickly the demand for different types of data center services grows. The service efficiency, so how quickly the energy efficiency to provide those services improve. It's the energy per teraflop. Power use effectiveness, which has to do with the data center itself, how much power from the data center is going directly to provide the IT services, and water use effectiveness, which is how the water consumption per unit of IT electricity improves. So the maps I'm going to show on the next several slides are going to show state level results for our reference scenario. And the graphs are going to show Virginia, the results for Virginia, which is currently the largest hub of data centers. And here we're looking at 2025 electricity demand, which is projected at about 0.2 exajoules in Virginia for data centers. But by 2060, we see the electricity demand for data centers has grown by about 5 times 2025 levels under the reference scenarios to 1 exajoule. But the range across these scenarios is really large, from 2 to 10 times 2025 levels over the next 35 years. Now looking again at 2025, we see that the share of electricity for data centers in Virginia is expected to be close to 35% in 2025. We don't have those numbers yet. With 4 other states, North Dakota, Nebraska, Iowa, and Oregon, having data center share of electricity demand in the range of 15 to 20%. But by 2060, Virginia's data center electricity consumption reaches almost 75% of total electricity consumption, with a range of 45 to 80% across the scenarios we looked at here. But an important thing that we want to emphasize here is that all of this electricity doesn't come from Virginia. Across the time horizon we looked at here, 60 to 70% of electricity is imported from other states. So the increase in electricity and consumption in Virginia for the data center expansion seen here, because I am in Northern Virginia, has implications for other states. And because the electricity generation mix and water availability varies across states, the increase in demand from Virginia will have varying emissions implications and potential water scarcity impacts across many states. So first, I want to look at, when we're talking about water use for data centers, that note that we have 2 different components. There's the direct withdrawals for the data center buildings themselves, which is the water used for cooling. And then the indirect portion, which includes water used for the electricity generation needed to run the data centers. Here we're looking at the direct cooling water, which is going to depend on the mix of data center types because they use different cooling technologies. And with smaller traditional data centers actually using cooling technologies that tend to be less water efficient than the hyperscale data centers. And this map is showing that the share of state level water withdrawals used directly in data centers for cooling is a really small percentage of total water withdrawals in all states. It's less than 0.5% in 2025. But on a local scale, on a finer resolution scale, this could be higher. And on the right, we see the total direct water withdrawals for data centers in Virginia, which is about 0.02 cubic kilometers. Why this isn't advancing. Okay, good. So over time, water use for data center cooling is expected to grow, though not by as much as electricity. Under the reference assumptions, only about 4 times as much water withdrawals in 2060 compared to 5 times as much for electricity. And this is partially because while both water and energy efficiency are improving, there's a more rapid increase in hyperscale data centers in these scenarios, which are, as I said, more water efficient than traditional data centers. But even with this increase, direct water withdrawals are still a relatively small share of withdrawals by 2060. So as I mentioned earlier, there's a second component to data center water use, which is the indirect portion for the withdrawals from the electricity consumed at the data centers. So remember that 60 to 70% of Virginia's electricity consumption comes from out of state, and the water withdrawal intensities vary across generation technologies, which also vary across state. So the indirect water withdrawals from Virginia electricity is the electricity production from in-state generation times the water intensity of the Virginia generation mix, plus the imported electricity times the water withdrawal intensity of the out-of-state generation. So in the large figure, we see that there's a dramatic decrease in water withdrawal intensity in Virginia in 2035 to 2040 timeframe, which is due to the decommissioning of 2 nuclear power plants in Virginia. Although I'll note that just a few months ago, those were the lifetimes of those were extended now to 2055 and 2060. So that will be updated in future runs. And because of the increased share of imported electricity and decreasing water intensity in state, for in-state generation, the out-of-state water withdrawals for Virginia electricity consumption become an increasing share of electricity withdrawals. So looking at the fraction of these electricity withdrawals used to power data centers, we see that the indirect water withdrawals are more than 200 times the direct withdrawals for cooling in 2025. And by 2060, the indirect water withdrawals in Virginia have grown quite a bit, but now there are only 70 times the direct withdrawals as the average water intensity of electricity consumed in Virginia has decreased dramatically, as we saw a few slides ago. And so that decreasing water intensity or improved water intensity causes a leveling off of total water withdrawals in our reference scenario. And as we add the option for on-site power generation, we would see the water intensity of data centers could change relative to the average water intensity for the electric grid. But that could also make the indirect data center water withdrawals become increasingly localized if they're generating electricity on site. So this research is ongoing. Our next steps include analyzing electricity prices, household energy burden, and in collaboration with the IM3 team, whose work Kendall's going to share in just a moment, we'll be exploring the implications for grid operations and siting constraints. We'll also be looking at things like the effects of data centers on water prices, water scarcity, and trade-offs across sectors. Critical materials that are necessary inputs to the servers and data centers are going to be explored. So within GCAM, we'll be able to explore the things like the potential for constraints on data center construction and services due to constraints on resource production or trade. And finally, a key development in this work is going to be to look at those two-way feedbacks on the potential for AI and future economic development through changes in GDP growth, jobs, and energy consumption, among other things. So thank you for your time, and now I'm going to turn it over to Kendall.
Get everything set up here. Someone confirm that they can see my screen.
Yep, we can see it.
Great. Okay. Thank you. Thank you, Stephanie. Hi, everyone. I'm Kendall Mongard, and I'm really excited to talk to you guys about all of the IM3 work that we've been doing over the last few months. This work was sponsored by Office of Science at DOE, as Casey mentioned. And I do want to acknowledge my co-authors here. I'm presenting on behalf of a larger team. This has really been a larger effort with a lot of different expertise. So we have Casey Burleson, Karam, Travis, and Jenny, and Chris Vernon as well. And it's been a very, very cool effort over the last couple months, and I'm really excited to go through the various results and analyses that we've been covering. So this project has two subtasks that has split into mostly focusing on grid stress for the task number 1, and then siting in task number 2. And I'm going to go through each of these and our various preliminary results and the modeling that went into both of them. So task 1 is really looking at, as we know, these data centers are going to lead to increases in electricity demand over time and into the future. What does this mean for our grid stress looking forward? And what does it mean for the actual demand growth that we're going to see under different scenarios? And then task 2 is looking at, well, we know that we have this huge electricity load coming online, but can we say something more specific about where? And then what are the additional implications for water built into that? If we can say, in the future, we think data centers are going to be located in these subbasins, in these balancing authorities, can we say more about the stress in those regions and try to pinpoint some additional impacts that way? And this has been a very fast-paced analysis, and a lot of our success has been credited to the flexibility of the models that we have under IM3. We've really been able to pivot a lot of the capabilities that are already built into these modeling capabilities to take on these data center attributes and actually model them in new and really interesting ways. And I'll go through the different models that attributed to each of these analysis in more detail in future slides. So starting with task 1, this is just looking at the grid stress component. Siting is in task 2. So to develop future electricity load growth due to data centers, we derived values from this EPRI report that came out that was a really nice report. And this task is led by Casey Burleson. And he found this report, and it's really cool because it breaks out 4 different load growth assumptions. You can see these different columns here going from low growth, which is about 3.71% growth annually, all the way up to this 15% higher growth scenario. And we like having this range because we can actually start to evaluate this this kind of bookend scenario of if we only see this 3% versus what are the grid impacts if we have 15% compounding growth there. And you can really see as they break down state by state what this starts to look like. This is the 2023 load. And in Virginia, you can already see in 2023, a quarter of all the state electricity demand was due to data centers. And so this report's really great because it breaks it out into each state and by scenario. And we can actually back out what these load growths will look like through 2035 and start adding it on to our own simulation results to evaluate what this grid stress is going to look like due to data centers. So this is showing the electricity demand outputs from our baseline experiments under IM3. This is an integrated experiment, and this is showing results from the TEL model, which is the electricity load model that Casey leads. And we have it broken out for each of our interconnections here, East, West, and Texas. And then what you're seeing here with the 4 lines are 4 of our scenarios. This includes information related to meteorological conditions as well as population growth assumptions. And you can see each of these correspond to one of our scenarios. We have 8 in total. There's just being just 4 shown here. And you can see what these look like. The top plots show the total energy demand and the bottom show the peak demand by year. And just for this analysis, I'm showing the moderately hotter, drier, and lower population. And what we do is we take those load projections from the EPRI report and we actually stack them on top of our baseline assumptions, which is showing the electricity demand without any data center assumptions added in. So this really lets us split out the difference of what these different load growth scenarios look like. And you can see immediately when you stack it on that it's a pretty big jump. So these lines here representing each of these EPRI scenarios all the way up to this higher growth scenario. And you can see when you line it up with our baseline experiment runs, it really jumps up. And we can look at this in two ways. To start, we can look at the total load growth in terms of peak demand. So going up to that higher growth scenario, we can see a plus 25 gigawatt growth from that additional data center growth. And then we can also look at it in terms of compressed demand in terms of time. So if you look across horizontally here and you compare to our baseline experiment, you can sort of draw a horizontal line and see, if we see this higher growth scenario, we're actually compressing 25 plus years of load growth into a decade. So Casey mentioned this a bit, but these data centers are coming online much faster than the electricity generation can be built, where natural gas facility, other types of facilities are going to take 10 plus years sometimes to come online, and these data centers are coming on much faster. So this is really, and Casey pointed this quite a bit, this is going to lead to grid stress. And do we have enough generation to actually meet these incoming demands, and what do we need to do to actually support the system? And then this was done at a balancing authority level, so we can actually evaluate the various levels of electricity demand as a fraction of the total demand in each balancing authority. And that's showing along these bar charts here with the percent on the y-axis. And you'll note when we look at some of these smaller balancing authority areas, this fraction of total electricity demand really starts to jump up, and in some cases is 40% or greater. And you've still got pretty high percent even for things like PJM, which is coming in around 12%. So all of this load growth information that Casey ran with the TEL model was then passed to our grid operations model. And this analysis was done by Karam Akdemir. And the GO model dispatches electricity generators to meet load demand. And we fed these EPRI projections modeled through the TEL model into the GO model to look at how does this impact electricity prices, unserved load, and other metrics within the Western interconnection. So this is the region that we're looking at specifically. And what Karam found was as we increase these different load scenarios, you really start to see these compounding impacts from grid stress. So what this plot is showing you is the marginal energy price on the y-axis for 2025, 2030, and 2035, and the number of hours that you're seeing that price for. And as you can see, in 2025, we don't see too much of an impact. But as you start to get out to 2035 and those growths are really starting to stack onto each other, we see that it starts to really push out, and we start to see average electricity prices by 2035 increasing 43, 47, 91, and 200% by the time we get into that higher growth scenario. And this is mostly driven by data centers exasperating prices during the most expensive 10 to 15 days of the year. In addition to just the baseline grid stress assumptions, we also evaluated various scenarios. And this first one is looking at what happens if we look at the range of retirements for different facilities that are going to happen by 2035, and what if we started to scale those back? These initial runs were done without any built-in new generation facilities, no new power plants were being modeled to try to keep up with this demand. So we try to simulate that a little bit by toggling different slates of retirement combinations, starting with 100% nuclear plant retirements. What if we just kept all of those nuclear facilities online through 2035, and then various combinations with nuclear, natural gas, and so on. And you can see the three metrics here. So we have locational marginal price, unserved energy demand, and unserved energy hours per year. And what we really started to see is you don't see it dropping to our baseline values of unserved energy until you get to the point of 50% natural gas retirements and or 100% nuclear plus 50% natural gas retirements. You can see it starting to drop below our baseline assumptions there. So that is a pretty substantial amount of generation capability that will need to be kept online to keep up with these growth assumptions, to be able to not see that unserved load that the model is showing under these different scenarios. And then another analysis that Karam also ran that I don't have a slide on given time constraints is a demand response analysis, where we essentially offered a price incentive to data center demands up to a 15% reduction of their power demand. And what we found with that was it was really a lot less influential than these planned retirements not happening. And ultimately, the outcome from that was you're still going to need to have new generation or not retire as many plants to be able to keep up with this energy demand. The demand response only had a minimal impact in a lot of cases. For the rest of the slides, I'm going to talk about task 2. This is the geospatial data center siting. I almost said power plant siting there because this is built off of an effort from our surf power plant siting model to actually geospatially site on a 100-meter resolution basis for this analysis, data centers looking forward using those same EPRI demands. So I led this analysis, and it ended up starting with a really in-depth literature review of everything we could find. So the whole motivation for this piece of the analysis was we know that there's going to be a substantial amount of grid stress, but can we pinpoint specific locations of where we think these new data centers are going to come online by 2035 or even beyond, so that we can start to say which balancing authorities, which subbasins are going to see greater water withdrawals, which public water supply systems might have increased water withdrawals and things like that. And to even begin this analysis, we needed to understand why are current data centers where they are? What kind of information can we glean from what they're putting out there, from their sustainability reports, from their advertisements in the case of co-location facilities that says they are going in this location because XYZ factors, so that we can try to understand and emulate those decisions in our modeling. And we found a lot of really interesting things based on cooling methods. This is from a Microsoft report. A lot of really specific things pointing to low electricity costs being a large driver. And then one really, really interesting case that I love to point out is the Switch Citadel campus, which is located out in the Nevada desert. And digging into this a little bit, it was a really interesting case because this is a huge data center, like multi-million square foot facility. And they chose to put it out in the Nevada desert because of lower taxes. It actually ended up being a cheaper place to site for them because of lower taxes, even though they wanted to access the Bay Area markets and the Los Angeles market, because they built this massive loop of fiber to still be able to access those markets. So you can see this blue line and the red line here that connect their two campuses and their markets. And it was a really interesting find because it really pointed towards the cost metrics that are really driving a lot of these decision making for these data center developers. So once we gathered all of that great literature information, we also wanted to compare against locations, geospatial locations of existing data center facilities. There isn't a lot of open source information out there actually about data center locations. There's a lot of proprietary information. There's databases that are sold, but we really couldn't find an open source database that was available. So we actually made one. We've also made this available, but this map sort of shows what the outcome of that comes from. These are derived from OpenStreetMap data, and we actually are able to break this down and extract square footage information so we can see what the relative size of all these data centers are. So this map is showing data centers as of 2024, and you can see the relative clustering of where these different markets exist. So we have the Northern Virginia market, which has been highlighted in the last two talks, but then you also see these markets in Oregon, in Washington, in Texas, Phoenix, the Atlanta area, and where they're really starting to cluster. And we can use this information to actually compare against our siting analyses, our geospatial layers, and determine what types of driving factors are really coincident with these locations. So the third step comes from this, and based on our in-depth literature review and where we're seeing existing data centers, we identified these six main categories of drivers for data center siting. And those ultimately come down to land availability and cost. These data centers, especially the hyperscale ones, are multi-million square foot facilities. In a lot of cases, you're also seeing data center developers will purchase large amounts of land and the land next to it because they are looking to expand in the future. They want to build the data center today, but they are also thinking 5-10 years down the line, they want to have access to the additional space next door. That means that there needs to be a lot of land available for sale, even better if it's not that expensive for them. They also need to be close to fiber network. This is a latency issue. They need to be able to deliver their products as quickly as possible. It gets very expensive the further out they are. Cheap and reliable electricity. This is a really big one. The highest cost for a lot of data centers comes from their electricity use. So you see them clustered in areas with lower prices, but also they're interested in areas that are going to be more reliable because those disruptions can be incredibly costly. They also need to have access to a water supplier. Most data centers use potable water for cooling, but there's also additional demands for drinking water and those working in the facility. So they need to be within relative access to a public water supplier so that they can actually get that water to their system. Tax rates and incentives. I've talked about this a little bit with that switched data center, but this really does come up quite a bit. You see various tax rates and incentives for things like they don't have to pay sales tax on purchased IT infrastructure. Various property taxes come into play, especially with larger facilities and things like that. So this is also a driver. And then we also looked at low natural hazard risk. You'll see advertising for they're outside of a large flood zone area, lower earthquake risk, things like that. So we found open source data sets that actually reflect each of these capabilities to try to emulate these decision making and try to constrain areas that we know these data center developers might be interested in. So here's just a couple high-level examples of what some of these look like, starting with the land availability and cost. This map is showing the Quincy, Washington area. It's in central Washington state, and the pink blocks are the data centers that exist from our database. And you can see with this land cover analysis, we can actually see where those data centers are developed. But this is just one example of we can use this land cover data to identify areas that new data centers might want to develop. This is a great location for data centers because there was an old industrial facility that has since shut down, and there was a lot of untapped transmission available. So you see these larger data centers actually clustering to this area. And so the additional surrounding area outside Quincy would theoretically be valuable land for new data centers. So we can actually extract that information from land cover. And this is at a 30-meter resolution. So it's a very cool data set that we're able to use. And here's another example looking at fiber provider service territory. So we ran an analysis and we found that more than 97% of all existing data centers are within a kilometer of a high-speed fiber service territory. So this is clearly an indicator that data centers tend to be in these areas, and we can use this information to actually build our composite siting suitability. And then same thing with power supply. These systems really want to be as upstream as possible. So we found that 76% of data centers are within a kilometer of a substation. They want to be as close as possible because if there is a disruption, they are less likely to be affected than if they were downstream. So we compile all of these different things together. Here's an example list of what might go into it. And you can see if you squint, these dots of black here are showing our suitable areas. Once we combine all of those exclusions, we're not letting it go in things like areas with excessive slope, areas too far from a public water supplier, areas with extremely high flood risk, things like that. And we get down to this composite at 100-meter resolution, and we can start to actually see these parcels of land that new data centers could, in theory, develop in because they are big enough space and they meet all of these qualifications that we've identified. And then from there, we build in this siting algorithm. And this is really the extension of our SURF power plant siting model, where we bring in the economics of it. So this is our locational cost. And this gets back to that electricity price, that property tax component that I talked about before, that really says in these available areas, how much is it actually going to cost to put it in that location? And then we have another factor that we're adding into this model that we're calling market gravity. And this is essentially, we know where there are huge accumulations of data centers currently, like Northern Virginia, Dallas, Central Oregon, Central Washington State, things like that. And we've built in this gravity model component to actually make it pull new data centers towards those markets, so that if you're a very small data center, you are highly incentivized to be closer to those markets. However, this also works in the way that if you are a very large data center trying to be sited, you have less pull because you are theoretically starting your own market in a way. You don't necessarily need to rely on things that are in that existing market. You are kind of the, in 2005, the first data center in Quincy went out there and they took advantage of a lot of really good infrastructure there, but it was such a massive facility that they were able to do that. And we can actually change the weight of each of these in our modeling. So we can say site 100% by locational cost. They don't care about being close to a market at all. And then likewise, we can set locational cost to 0. We just want them to site as close to market as possible. And this has been a really cool component because we can actually look at a range of scenarios here in combination with our range of scenarios of data center growth. And that's exactly what we did. So we came back to this EPRI report and we actually extracted how many data centers under an assumed size, power usage, efficiency, things like that, IT infrastructure. How many data centers do we actually need to site in each of these states for each of these 4 scenarios? And we run the model in the suitable locations and determine the lowest cost, also factoring in that market gravity component, determine where they might go. So I'm only going to show the bookend scenarios here, starting with the low growth. So that's the 3.7% annual growth. And you can see on the left here, this is a siting scenario with more weight being put on locational cost, only 25% on market proximity, and then a 50-50 split on the right here. So a little bit more weight on market proximity. It's harder to see here than it will be on the next slide for the higher results, how that market proximity comes into play, but I'll point that out in a minute. And we can see right off the bat where data centers are starting to go. They're already clustering towards areas that have high markets, but you're also seeing ones going into locations that are maybe new markets, taking advantage of things like low energy prices and open land and things like that. And you can see the variety of cooling types that we consider as they come on. So these dark blue are purely water-cooled systems. The bright yellow are located in areas where the water stress is, or the baseline water depletion is high enough that they would, in theory, not be a water-cooled system. They would mostly be mechanically cooled, similar to an HVAC in your home type system. And then we have others that are mixed, and that is a part of the year they might be mechanically cooled, part of the year water-cooled, things like that. This next slide is showing the other bookend here. So this is our higher growth scenario. So this is the 15% annual growth through 2035. And you can immediately see that it is substantially more data centers than our low growth, especially in states like Iowa, Illinois. In Texas, you see less on this map because they're so clustered together, but it is a substantial amount of growth that you're seeing. And I like this slide because it really starts to illustrate how that gravity, that market gravity component starts coming into play. If you look, for example, at states like Illinois, if we make the market more important, if we add more weight onto that factor, they really start collapsing in towards Chicago. And then you can also see this in states like Pennsylvania, where under this lower market importance, we see a new sort of data center market starting in Pittsburgh. But the second you add it in under higher importance, it really starts to collapse more towards that Philadelphia area. So this really illustrates a cool example, and the same thing around Phoenix area. There's a lot of cheaper locational cost areas in Phoenix, or sorry, in Arizona. But if you make the market more important, they really start to collapse in, and you see more data centers also being mechanically cooled because they're now putting more value on being as close to the market as possible. But they are now, due to water stress in that region, more likely to be mechanically cooled rather than water cooled. So from there, and this is what we're working on right now, using those projected locations of data centers into the future, we're able to look at what the water implications are. So this is showing the increased water demand by subbasin across the US for the low growth scenario and higher growth scenario, using the higher weight on locational cost scenario as well. And you can really see a pretty substantial difference in the impacts in growth here. So while there are some subbasins in the low growth scenario that still see some big jumps in total water demand due to direct cooling, you also see those same ones plus a huge amount more in the higher growth scenario, especially in states like Oregon, California, Bay Area, more subbasins in Texas, and then Virginia, of course. And where we're going from this is conducting additional water stress metrics. So this is just showing net increase in water demand based on the cooling type and the size of the data center that we're connecting and where they're going. We also want to evaluate this against the water stress in each of these subbasins. So even though, for example, you're seeing a huge amount of water increase in Virginia, if there's more water stability there, that may be less impactful than maybe some of these other ones in the West that even if it's a lower amount in aggregate, if they have a higher water stress baseline, we're going to see a huge impact there. And we're also going to look at indirect water use as well. Stephanie touched on this, where we're interested in, hey, we know there's a bunch of mechanically cooled data centers in our results. What are the indirect water use due to the electricity generation of those facilities? So that's what we're going to be working on next, and we're really excited to get those results out. Another thing we're doing, I mentioned this open source data center database that we built. We have made it available and as part of an interactive dashboard, which is really cool. Here's a screenshot. And this is showing all of our database or data center locations in our database. And then we're also showing a lot of supplemental information that I talked about as potential drivers of data center locations. So you've got things like transmission lines, municipal water service areas, and high-speed fiber providers, and how many there are. So this is a very cool dashboard. This has just been released, and it allows you to zoom in really far and look at a lot of really interesting areas. The Virginia area, for example, is a very cool one. You can see a lot of detail there and just how many data centers are really clustered in that area. And I believe they call it Data Center Alley, and something like 75% of all internet traffic flows through there. And once you zoom in and see all those data center buildings, you can kind of understand that a little bit more. So I've covered a lot of information. We've really hit the ground running with this analysis over the last few months. And so we've covered quite a bit. We've built a lot of new cool modeling capabilities as part of it and run a lot of neat analyses. But I do want to just leave you with a few high-level conclusions. Data centers are going to significantly accelerate load growth in all three interconnections. It is both going to be an increase in peak load, but also can be thought about of shrinking the timeline of how fast that growth comes online. And then compared to our base case scenario, we see substantial increase in electricity prices and unserved load across the Western interconnection through 2035 due to data centers. And really only by postponing 100% of nuclear and 50% of natural gas plant retirements do we really start to account for all of that load growth impact and bring it back down to our baseline assumptions, which don't incorporate the data center demand. And then last, we're finding what really drives new data center development. And we're finding that electricity prices, access to water, fiber providers, proximity substations, and existing data center markets are all really big drivers of where we might see data centers coming online in the future. We know where the data centers are coming potentially in the next 1 to 2 years through headlines and things like that. But this is looking out to 2035. What are the areas that may see under these really high growth scenarios where these new clusters might be, where these new markets might form, and we can really start to pull out additional analysis from there and cool insights, both for the electric grid and for the water system. So I will stop there, and I think we're going to shift to questions. Thanks very much.
All right, thank you to the speakers. So at this stage, we're going to have a pretty open forum, so you can put questions in the chat. You can also raise your hand if you have specific questions for specific speaker or across the panelist speakers. I wanted to just kick off with a preliminary question across the speakers. Just the sheer degree of uncertainty when you leave the next 2 to 5 year horizon. For each of the speakers, where do you think the critical points are to focus on in that space of uncertainty, in terms of where you think things are really going to be fundamentally important to understand on what trajectory we're on? I guess it maybe makes sense to go in the order of how you presented.
That's a good question, Pat. I think in my mind, where these things are going, how big is it actually going to be, right? The EPRI scenarios showed a wide range of potential growth rates, and from Kendall's results and Karam's results, it really takes like an above average point in that range to see grid stress start to emerge. And then I think maybe the more interesting question is who pays for these upgrades, and who bears the burden of the uncertainty from the cost perspective. If you plan for these things and they don't materialize, So somebody's still got to pay for that, and I think that's an open question that the industry is trying to grapple with right now.
Sorry. I think one of the things we're really trying to get a handle on is what is the demand going to be for the services that are provided by the data centers. So as Casey said, if you're planning for them and they don't materialize, is that because the demand's actually lower than we expected it to be? So that is really a key component of it. And another part is the efficiencies of the technologies. If you have a large demand, but you're able to meet that with more efficient technology that uses less water and less electricity, then you also may not see as much need for electricity expansion, but it could go the other way as well. So lots of uncertainties.
I concur with the lots of uncertainties. Yeah, and iterating Casey's point, I think the range of demand here is a huge unknown because I showed one of the maps there, really, really different worlds that we could live in depending on whether it is that 3% or 15% annual growth. And then another factor that's uncertain is you see some of these communities that start to develop plans and zones for putting new data centers in, saying, hey, we're going to build the transmission infrastructure to that zone, the water infrastructure to that zone, but then you build it and they will come. So how much of that planning is going to happen? Or is it going to be more regional planning and things like that? Or is it going to be kind of a Wild West, every small town is going to try to incentivize siting to their locations and things like that. So there's a lot of unknown on the planning side as well.
Thank you all. We actually have a question in the chat from Angelo Gergel. I don't know, Angelo, would you want to unmute and ask your question?
Sure. Can you hear me?
Yep.
Well, first, I would like to congratulate you all. I think the work is amazing. It's very nice how much you guys did in few time to try to understand a little bit better this problem that we have, right? And I would like to know more how you guys are thinking on how to represent the side of positive impacts from the data centers and AI and all those things. How do you envision to put that in GCAM, or how you think, what are the assumptions that will drive how much the economy will benefit from those things? Since we also are thinking about those issues. So what are your takes on that?
Thanks. I was typing an answer, but it's good to talk through it. That's something that we haven't started yet in terms of putting it into GCAM, but it's something that we really recognize the importance of. That not only is there a demand for these services, but the services are providing something. That there's a reason people want them, and one of those reasons is it can make people more efficient at their jobs. It can make the grid more efficient. I don't think that we would claim to have all the answers on exactly how that's going to unfold. But we've started looking at the literature and seeing kind of what estimates are out there. And clearly it's going to have different effects in different parts of the economy. I think one of the big things people have already seen an effect of is on computer programming. That, from what I've seen, there's actually a decrease in the number of job postings for entry-level data programmers because people can do so much more with AI that there's less of a need. Will that continue forever? I don't really know because, junior level people now become mid-career and senior level people later. So you need somebody to fill those roles. But there will be transitions. So it's going to be exploring it through a lot of scenario analysis and seeing what other experts say.
Excellent. So again, happy to get questions in chat, or if you want to raise your hand. And I'm going to take the moderator privilege while we're waiting on questions. Sort of looking at Kindle's results, but I'm happy for everyone to ask. Just in brief, this cost versus localization and market has a pretty huge effect on compounding existing demands, both on the water and energy side. And then there might be some implications in terms of how much of that goes into the retail energy market and the consumer. It seems like that's a pretty big issue in terms of the localization. I don't know if that's a clear question, but it seems like it's a huge difference whether it's city-driven, market-driven, or cost in terms of the land resource, and just what the implications would be of that.
Yeah,
Yeah,
one
Kendra?
of yeah, one of the analysis, because you're completely right, and you could see it, especially in that higher growth scenario, how much they really start to collapse in on those larger market areas. One of the analyses we're going to run is across a range of weights. Are there areas where we see sightings regardless of weight? And what can we start to say about ones that, like, hey, this area is great for locational costs and it's near a market and you're going to see sighting there no matter what. So we can actually break it down into kind of almost approaching a likelihood of this is more likely to see sighting because it shows up across all of our scenarios and the range is there. Is that getting at your question a little bit?
Yeah, I think the other side of the question is sort of, it seems like there's pretty broad implications of concentrating the infrastructure in a very tight cluster in an urban zone versus spreading it out. And then the other thing is what, smaller communities could handle if it's spread out. But maybe
Right.
I'll pass to Casey or Stephanie to see what your thoughts are.
I think it's a really interesting open question. I also think it's something that, we have just a few years of data on where these things are going, because the explosion really started maybe 2 to 3 years ago. So if we go 2 to 3 years from now and look at some of the maps that Kendall generated as far as like where data centers are, we could have a completely different view of the world than what we have now based on the limited insight that's available from the data now. So it's a highly, if we think about these models as uncertain parameter models, I would say that this is a highly uncertain parameter that would lead to drastically different outcomes in our modeling.
We do have a couple questions in the chat, but Stephanie, if you had anything that you'd like to add.
I don't have anything to add beyond what Kendall and Casey have already said. Angelo's question, I don't think I'm the best person to answer how easy it would be, but I will say that I know they are extending the permitted lifetimes of nuclear power plants. I think I mentioned that in Virginia, they just extended the ones that were slated to go offline in 2035 and 2040 by another 20 years. So, and that seems to be a fairly common occurrence from the experts I've talked to. But I think perhaps Kendall or Casey could add more on that.
Yeah, I'm not a regulatory expert in this space, but all you have to do is Google it, and you can see that like this is already happening in the Eastern Interconnection, where they're delaying these retirements, primarily of nuclear and natural gas, but of some other resources as well. It's happening. So like this isn't a hypothetical scenario. It's something that's happening in real time.
And there was additionally sort of a question on sort of the diversity of the energy portfolio. And I guess there's a couple facets of that. Is some of the data centers are being constructed such that they have sort of their own site generation and different modes of generation versus sort of broader regional or national development of diverse portfolios of energy. So maybe you all want to comment on that.
Yeah, I can talk about how we modeled this in IM3 to date. So the grid results that Kendall showed, there's a couple of assumptions that are underpinning those. One is we're not building any new generators explicitly to meet the data center demand. So there are new generators in those scenarios, but they were built in the scenario to meet sort of that background load growth. And the reason of that is purely the timeline, right? By just looking at the next 10 years, if you started today, it would be somewhat challenging to get a new nuclear plant online and interconnected in the next 10 years. Natural gas maybe a little bit faster. So maybe by 2035, you could get some natural gas online, but like the timescales just don't match. So we weren't building new generators to meet that. As part of task 2 that Kendall was talking about, where we look at more explicit data center siting and looking at where they may go in different parts of the country. One part of that would be to explore co-siting generation. So when you build a new data center facility, you could also look for regions of land that are suitable for different types of generators. So like if you wanted to co-site a data center with a natural gas plant, we know that there are lots of siting restrictions around natural gas. And you could narrow your search window down to just the areas where you could build a data center and then natural gas directly alongside it. So that's part of that task 2 looking forward. And that's something that they're also exploring, right? If you look at the news reports coming out, a lot of these are either siting directly alongside existing generators or building in places where they could build generators alongside those, because they want to be as close to the generation as possible to minimize the disruption of outages. Yeah, I guess the final thing I'll say there is like we do intend, once we get the siting results from Kendall and her team, is to rerun those grid stress simulations with the precise nature of the location of the load more prescribed, and see if that has any implications, like Pat talked about, the clustering of the load potential into these concentrated urban areas. That would have a lot of implications for things like transmission congestion as well, right? Like if you're putting all your eggs in one basket, you have to push a lot of power through the line supporting those areas, and that would change how the transmission build out is done in the future.
So in GCAM, we haven't currently constrained the rate at which power can come online. So in the scenarios that I showed, it's the new generation is meeting the demand, but that's going to be a next step for us to look at. And one of the things, these 2 projects will be coming together in some ways. I think there's, a lot of different ways that we can bring the different models together. And one of them is using some of those siting constraints from SURF that Casey was just talking about in GCAM to limit where you can build the power plants, but also instead of just making it a purely economic decision in terms of on-site versus grid produced electricity, you can add those additional constraints as well that Casey was talking about. So we can utilize a lot of the information coming out of this much more fine-scaled resolution modeling in GCAM as we look at the potential for expansion. And then, as I think Jenny mentioned in the chat earlier, it can also go the other way, where exploring the scenarios of expanded demand for data centers, and then from GCAM into some of these IM3 models. So yeah, we hope to do a lot of that work jointly going forward.
Yeah, thank you all. Again, we are actually scheduled to 2:30. We don't have to necessarily, but if you have a question or a comment, it's welcome. And so there's a statement from Dale Rothman that you look at the potential impact on prices. And that's an affirmation, yes. I kind of want to, I think water is getting a little bit less, and I think somewhat reasonably, emphasis, but the institutional elements of gaining access to even small levels of increase in consumptive water can be quite challenging, especially if it's centered in locations in the West where you have certain water institutions that have to be navigated. Just sort of your thoughts there on where you see that interface between the energy and the water, where you see the modeling challenges, and also where you think even if the volumes aren't as dramatic in terms of percentages of change relative to the electricity storyline, it's still potentially significant depending on the scenario, and I think institutionally and from an infrastructure investment perspective, significant. So just open the floor on that. Whoever would like to take it first.
I don't know if Tom Wild is on my colleague on one of my colleagues on this project who's definitely particularly interested in the water side. I don't know if he's
Tom's on. Tom, you're welcome to unmute.
gonna say anything. Can I put you on the spot?
I'm here. Can you guys hear me?
Yeah.
Yeah. So I think you're highlighting an important issue, Pat. Certainly, I think we'll see that there are, regions of the country, like Virginia, that are hotspots where in the future we might in fact see that the level of water usage, even statewide at a core scale, is actually quite high relative to other uses in the economy. So there'll be places where there really are serious water issues to sort out. And then there'll be places where, where the stress is kind of more local, is placed on municipal systems, for example, in particular areas. We're also, we're seeing dynamics that are hard for us to model, like, like data center developers kind of ponying up cash to help build up or upgrade or retrofit existing municipal water facilities so that they can kind of gain preferential access to that water, which is of course not something that we easily model, but it sort of gets at one of the points you were raising about water rights, which is that actually gaining access to the water that's needed, even if it's small, if it's competing directly with particular other uses of municipal water, could be quite challenging to get access to that water. So yeah, I think it's not probably the point where, at least on the GSIM side, where we started, but I think it's going to be a really key issue in some places and both at a core scale and a fine scale. And I think we're going to see the indirect component continue to be an issue as thermonuclear generation persists.
Just to
Thanks for
add
jumping
on
in, Tom.
to,
Yeah, go ahead, Kendall.
I was going to add on to something Tom mentioned about these data center developers investing in the municipal systems that they're going into. And there's numerous examples of this across the country. And one that comes to mind is the Dalles in Oregon. Google went in and built a massive data center, and part of their deal was they invested in a multi-million-dollar project to redo their water system and add more groundwater storage for the city. And so the increase overall was a net positive for the city, but the part of the deal was that they get most of that water for their facility. And you see similar examples of this, like an article that Casey sent my way this morning in Tucson. They built an 18-mile pipeline to connect to the water system. And you see the same thing in Reno, the same Switch Citadel system built a really long pipeline to pull their water in. So you're seeing investment in these water systems to try to kind of pull as much out of it as possible. But it's definitely these local towns are seeing these massive organizations, the Googles, the Microsofts, come in and foot the bill for these infrastructure upgrades. And then you see other data centers that actually then tend to move into those areas to try to take advantage of that improved system as well. You see this a bit in Quincy, Washington too. They just built a water treatment facility to actually feed water into the data centers there, and it limits where they can put specific data centers to build into that pipeline system that was built. So a lot of really interesting infrastructure investment happening in that space for sure.
So with that, we're in our final minutes. Happy to give each of our speakers your your final thoughts as we sign out.
I'll just say, like, it's been super interesting to work on this project. It's one of the most stimulating things that I worked on, and I think it's a really good example of showing how the MSD community can pivot when needed and can move quickly to address sort of really pressing challenges that are facing the country. So I think it's just been a fun project to work on, and we're happy to share it with you guys.
Yeah, I'll second that. This has been a incredibly interesting topic to work on. And you know, I am really fascinated by, you know, where the demand is coming from and how it's going to interact with the future economy. And again, we don't know the answers to that, but exploring some of those scenarios is going to be really, really cool, in addition to the water and energy impacts.
I will third how interesting this has been to work on the last few months, and it's been really fun to really push the flexibility of our models and learn new capabilities to really expand what we can do with these multi-sector tools.
Well, I would say it's been fun to listen to the results, and I appreciate the time invested from our audience and from our speakers. And with that, we'll go ahead and conclude the webinar. Thank you, everyone.
Thanks for inviting us, Pat. And thanks everyone for listening.
Thank you.
Thanks, everyone.
Bye-bye.